All right, hi guys. Welcome back to my channel. Today I'm gonna do review for the nuclear chem unit, which is unit 5. I'm not sure how long I'm gonna be able to talk for, so I'm just gonna try and do the first page. See how that goes. If I'm not dying of thirst by then, I will continue on to the next page. By the way, at the point where you watch this video, we might not have gotten to all of the topics in class. So if you don't know what I'm talking about for some of the questions, don't worry. By the end of the unit, you'll be fine. But anyways, let's just get right into it. So the first one, which nuclear equation represents a spontaneous decay? So again, remember that sorry, oh wait, I need to put on the marker. 1 second. Annotate. Feeling purple. Okay. So again, remember that a spontaneous decay is going to be alpha, it'll also be beta, and it can be gamma. All right. So basically that's what we have to look for here. So the first one, I can automatically see that this one is an alpha decay. So I know that this is going to be the correct answer, but I just want to make sure that none of the others are beta or gamma or alpha. So I see over here for B, we have aluminum 27 being bombarded with an alpha particle. Again, remember, the telltale sign that you have a artificial reaction is if you have two reactants. So this one doesn't count. This one is basically a fission reaction. You're taking uranium-235 and breaking it apart into smaller and lighter nuclei. This also doesn't count. Fission and fusion are both artificial. And this one, you are taking lithium-7 and bombarding it with a proton. Again, two reactants on this side. This one is artificial. So our answer should be choice A. All right, let's get rid of all this. Okay. Next one, which nuclear emission has greatest mass and the least penetrating power? So again, the particle that has the highest mass is, sorry, bear with me guys as I try to navigate this pen thing, is the alpha particle, which has a mass of 4, charge of 2. So this is the one with the greatest mass off the bat. And also it has the least penetrating power. Again, the order goes alpha, beta, gamma, and neutron. Least to highest. Okay, so this one should be an alpha particle. Choice A again. All right, number 3. Which list, so this basically goes right into what we were just talking about. Which list of nuclear emissions is arranged in order from the least penetrating power to the greatest penetrating power? Again, penetrating power is basically how easily an object or a particle will go through another object. Again, you don't really need to memorize it because if you just look at your reference table, let's actually take a look there for a second. So if you look at table O, all of your particles are listed for you. Okay, and they're actually in order, basically, of least to highest penetrating power, starting with alpha. So this is the least, and neutron is the highest. This is, beta is somewhat medium. Oop, that was supposed to be an arrow. So it goes from least to highest, and again, protons and positrons don't have any penetrating power at all, so it doesn't apply to them. So if we go back to the question, they want least penetrating power to the greatest penetrating power. Okay, so this one is just basically in alphabetical order. So again, we should go with choice A. Alpha has the least, beta, medium, and gamma pretty high. Okay, neutron is the highest, but gamma is also up there. So out of this list, we would want to go with choice A. Okay, next one. So we have a nuclear equation here. So we're basically just filling in X, and remember that we always want our mass numbers on both sides to balance, and we also want our atomic numbers to balance. So it's kind of similar to a math equation. Everything on each side of the equation should always be equal to each other. So over here, our mass number totals to 232. Over here, it's only 228. What do we need to add to 228 to get to 232? That would be 4. Down here, our atomic number on the product side is 88, but we really need it to be 90. So we need a 2 here. What particle has a mass of 4 and charge or atomic number of 2, that would be an alpha particle, or it can be rewritten like this. Either way, this is an alpha particle, and this is representing alpha decay. All right. This is basically the opposite of question 3, so just in the opposite order. So which list of nuclear emissions is arranged in order from greatest penetrating power to the least penetrating power? Again, lowest is alpha, then you've got beta, then you've got gamma, and then you've got neutron. So they want the greatest to the lowest. So we would want to start here with gamma. So A and B are out. Alpha has the lowest. We want to start from the greatest and go to the lowest. So we want to start from gamma, then it should be beta. So we know it's not going to be C, so it should be beta, and then it should be alpha, which we see here in choice D. All right, number 6. Which particle has a negative charge? Again, if you can't remember this, just make sure to go and use table O, all right? Now, A and C might throw us off a little bit. We spoke about ions a little bit in unit 4. We will get way more in depth with this in unit 7, which is chemical bonding. However, we did go over the fact that metals, which lithium and aluminum are both metals, metals like to lose their electrons, which gives them a positive charge. So metals typically end up becoming cations. So we want something with a negative charge, so A and C don't make sense. Alpha particles we know have a positive 2 charge. So our only option is the beta particle. Again, it is basically a high speed electron. You can write the symbol for a beta particle like this, or you can write it like this with the actual beta symbol. Alrighty. Number 7. An electron has a charge identical to that of, and we literally just went over this one. Again, an electron is basically a beta particle. Beta particle is just a very fast moving, high speed electron. Again, write it like this, or you can write it like this. However you prefer to write it, it doesn't matter. Either are valid. Both can be found in your reference table as well. So you don't even have to memorize those. All right, number 8, we've seen this plenty of times before in class. So we have this radioactive source right here, okay, in this little box on the side, emitting radiation, which gets deflected as shown in the diagram below. So we have 2 electrodes here, one positive, one negative, and we can see that the path of this radiation is being bent upwards towards the positive plate. Again, opposites attract. So the only thing that would be attracted to this positive electrode would be something with a negative charge. So let's go through our options. For A, I see that I have an electron or a beta particle. So I know that this is ultimately, where did this go? 1 second, sorry. This would be the one that I would want to go with, okay? Because I know that opposites attract. So the thing that is getting attracted to the positive electrode has to be negative. Alpha particles have a positive 2 charge right here. So that doesn't count. This is basically a proton. Protons have a positive 1 charge. That doesn't count. Neutrons have no charge. So a neutron would just go straight through and not be attracted to any of these electrodes. So it's not D either. Final answer should be A. A lot of A answers here, I'm noticing. Okie dokes. Number 9. Given the reaction, this reaction is best described as, this one is very nice and simple. This one is simply a beta decay. We can see right here that we've got a beta particle right there. Okay, again, if you can't remember what the particles are, simply use table O. So I would go here. I would see that in that equation, I see this symbol being written. So I can see that it's a beta particle. So I would know that it would be beta decay. So choice B should be our answer. Number 10. Which emission will be released from an unstable iron 53 nucleus? Once you hear something like this, which type of emission, okay, or what type of decay is something going to go through, you're not supposed to just know this off the top of your head. So you should go automatically to table N right here. Now what we want to do is we want to find iron 53, and it's right here. And I can see that the emission that it's going to give off, that is basically its decay mode right here. 1 second, let me get the pen. right here, decay mode, that's what we want to pay attention to. And for iron 53, I can see that it's this little beta particle with a positive sign. Again, that is not a beta particle. It's not an electron. That is an anti-electron, okay? So it's kind of like the antimatter. So this is an electron basically, but with a positive charge. It still has no mass, but its charge is exactly opposite that of an electron. Instead of -1, it is a positive one. So this one would be a positron. All right, let's go back. So our final answer for this one should be a positron. Again, it was that little symbol, the beta symbol with a positive sign. All right, number 11. Which radioisotope has an atom that emits a particle with a mass number of 0 and a charge of 1? And we just went over that one. Again, particle with a mass number of 0 and a charge of +1, that is a positron. Again, you can write it with the beta particle symbol, with the beta symbol, or you can just write it with the electron symbol. Either one of these is good. So we're looking for what radioisotope basically undergoes positron emission. So again, we have to go back to table N and we need to compare all of these and see what their decay modes are. So let's go back here. So that first one was hydrogen 3, and we can see here that it has a beta particle decay mode. So this one doesn't work for us. So it's not the first option. The next option was nitrogen 16. And I can see here that it is also beta decay. So that one also does not work. Next one is neon 19 right here. And I can see that this is the correct one. This one is a positron. So this one would be positron emission. Let's just make sure. Okay. Plutonium 239, that's alpha decay. So that one also definitely does not work. So for this question, we would want to go with neon 19. That is the radioisotope that undergoes positron emission. And again, we figured that out from using table N. All right, next one. Number 12, which statement best describes gamma radiation? If you can't remember, again, use your reference table. It's here to help you. Gamma radiation has no mass right here at the top, and also has no charge. Okay, so let's take a look at these options. Mass of 1, no, doesn't work. It's got no mass. So it's really between B and C because D also says that it has a mass of 4. This is describing an alpha particle. No, choice A is describing a proton. That's a P. B, it has a mass of 0 and a charge of -1. This is describing an electron or basically a beta particle. And C, mass of 0, charge of 0. This is definitely a gamma radiation. Okay, so we would want to go with choice C. All right. And again, this is another related question as well. Which nuclear radiation has high energy and no mass? So this is the gamma radiation. Again, gamma radiation is kind of like high energy X-rays, very dangerous to any living organisms. You don't want to be around it. Okay. Alrighty, and then our last question for this page. Based on table N, uranium-238 and uranium-235 have different what? So let's go over to table N. And I can see here, let me get the pen. So we are comparing these two. Okay. So the decay modes are the same. They are both alpha. Since they are both uranium, they should also both have the same protons. They are the same element. Again, any atom of the same element is going to have the same number of protons. Their atomic numbers should be equal. Their number of electrons should also be equal. These are neutral. They're not ions. They are neutral. So they should have the same number of electrons. Okay. But what is clearly different is these two values, which if we scroll up, we can see that this is the half-life. At this point that I'm making the video right now, at least we haven't gone over half-life, but their half-lives are different. meaning that they will decay at different rates. So for this one, we would want to go with choice B, half-lives. All right. All right, guys, let's just keep moving on. I think I'm good to move on. Number 15. Which of the following radioisotopes has the shortest half-life? So again, we're going to want to go to table N, and we're going to want to look up each one of radioisotopes. So we can look at, first one was carbon-14, has a half-life of about 5,700 years. And again, we're looking for the shortest half-life. So this is the highest one so far because the first one. Hydrogen-3, 12.31 years. So automatically carbon-14 is out. Hydrogen-3 has a much shorter half-life. Next one is potassium-37 right here. This has a half-life of 1.23 seconds, so an extremely short half-life. So right now that's our winner. Let's see if phosphorus-32 beats that. Phosphorus-32 right here, 14.28 days. That does not beat out for the shortest half-life belonging to potassium-37. So that is the one that we would want to go with. All right. Number 16, and I'm probably going to stop at question 17 or 18 because my computer is dying and my charger is nowhere near me. Anywho, next one. This is a half-life, and there is my low battery warning. Thank you, Mac. Okay. So we have an original sample of some radioisotope, and it originally had a mass of 10 grams. I'm going to work up here a little bit. So it originally had a mass of 10 grams. After 2 days, 5 grams of the radioisotope remained unchanged. What is the half-life of this radioisotope? So this one is real simple because we're going from 10 grams, and regardless of what its half-life is, after however long its half-life is, okay, half of it is going to decay. So after one half-life, you should have 5 grams. So we can see that after 2 days, we've got 5 grams. So that means that the actual half-life is just 2 days. So this one is B. This one is a very simple half-life problem. Let's move on to the next one. All right, number 17. What is the number of hours required for potassium-42 to undergo 3 half-life periods? So what we need to know is how long is one half-life for potassium-42. So we need to go to our table N, look up potassium-42, and I can see that it has a half-life of 12.36 hours. So what this means is that every 12.36 hours, half of our sample of potassium-42 will decay into some other isotope. So again, 12, let me write this down. 12 point, that does not look like a 12. 12.36 hours. So what is the number of hours required for potassium-42 to undergo 3 half-life periods? So this is 1 half-life period, so all we gotta do is just multiply by 3. And we should get 37.2 hours. So this one should be choice D. Let me see what my percentage is. Oh no, it is 5%. Okay, let's do one more. Or let's try to get to 20. That would be good. Okay, number 18. If 3 grams of strontium-90 in a rock sample remained in 1989, you know what, actually, I'm gonna stop it here. So this video will just be questions 1 through 17, and then I will make another video for the next, 20 or so questions. I really hope that this was helpful. And again, I will make the other videos. I really hope that you guys watch this. And also, again, please don't sit here and do all of the questions at one time. It is a lot of questions. Do a few questions every single day, and you should be fine. Anyways, I'll see you in the next video.